draw the correct Lewis dot structure for each. The 3D structure, try to draw, like we did on the board, the 3D structure, and name the electron cloud geometry and the molecular geometry. So what do we have to do here? Well, the steps were find the total number of valence electrons. Well, carbon has 4, hydrogen has 1, and each of those fluorines have 7, so that'd be 21, 22, 26 valence electrons altogether. I'll assume carbon is the central atom, and I'll put an H, a couple of fluorines. I've used 8 of the 26. That's leaving some left over. Next step was to fill up all the outside with either the full octet, as fluorine needs, or in hydrogen's case, it only has room, it doesn't get to the second level, so it only needs those 2 electrons. I have now used 8, 24, 25, 26 electrons. All electrons have been used. That is the Lewis dot structure for CHF3. Okay, the electron cloud shape, well, there are 4 regions coming out of the carbon. That means there are 4 pairs of electrons, which we now know the electron cloud shape becomes a tetrahedron, or tetrahedral. Okay, there's that one. The molecular geometry. Well, I'm going to try to draw this. Well, actually, I can do the molecular geometry because there are no lone pairs. Each carbon has a bonded atom on it. So the molecular geometry has to be the same, tetrahedral. Okay, I'm going to try to draw a 3D structure of that because it helps me see if I can decide if it's polar or not. It definitely could be polar because it has one of our electronegative atoms in it. Remember, fluorine, oxygen, chlorine, or nitrogen. It has one of those 4, so this could be polar, but it depends on the 3-dimensional shape also. So I'll try to draw this. I'll say there's carbon. I have 4 sticks coming out, so I'll have hydrogen come up here, a fluorine come out, a fluorine come out, and then be another fluorine going back into the paper. The electrons would be pulled towards the fluorine because they're the most electronegative, and I can see that that would leave a negative side and a positive side, and right there, if I can imagine this little plane slicing through, I can see there's a negative side and positive side to the molecule. So this is a permanent dipole, and it is polar. Now let's look at CO2. CO2 has 4 electrons, and 2 times 6 is 12. That's 16 electrons altogether. We did this one in class. So the first next step is to connect those, put the electrons on the outside, but I've used all 16. Carbon does not have a full octet, so that in that situation we take electrons and we make double bonds, and that creates this. A double bond to an O there, and a double bond to an O there, with those pairs sticking out. The central atom, carbon, only has 2 pairs of electrons coming out. That would make the electron cloud geometry linear. And also, since there's no lone pairs on the carbon, the molecular geometry would also be linear. Now, it does have oxygens. Since it's linear, I don't really have to try to draw a 3-dimensional picture. It's just a line. And we learned in class that even though this side's kind of negative, and this is kind of positive, and this is kind of negative, and this is kind of positive, there's no plane of symmetry that allows us to have a positive negative half. So we would say this is nonpolar. I guess I should have stated that this one up here was polar. Okay, that's the first page. The second page. The Lewis structure for water, and show why it's bent and why it's polar. Okay, that's a really important problem for this class. The Lewis structure we've done in class enough times, so I'll just put it. Looks like that. Okay, those are 2 dots. So why is that bent? Well, because the electron cloud geometry is tetrahedral. But since there are 2 lone pairs, the molecular geometry is just this sort of bent part. So the molecular geometry is bent. Okay, so there's why it's bent. Okay, now why is it polar? Because oxygen is electronegative, so this side's kind of negative, the sides are kind of positive, and we have that plane of symmetry. Okay. Next, these things like water, this particular one had a permanent dipole because the way it's shaped always gives you a positive and negative end. Or another option that could happen is you could just have something like oxide ion where the whole thing is a single object that is negatively charged. Okay, so that's not a dipole, that's just a charged object. Those things would attract each other because that negative thing would still be pulled to one end. Other polar molecules would be attracted to the polar water. So you have a couple ways that forces can happen in between molecules or between particles. This force would be a charge being attracted to a dipole versus a dipole being attracted to a dipole. But these are all permanent situations. In class, it's hard to see with this picture, we demonstrated if you rub a balloon on a shirt, if we assume the balloon picks up some negatives, then the shirt is now positive. And we brought the balloon near the wall, and we saw, and it's hard to see in the picture here, that the wall, the electrons in the wall squished away from the balloon. That created a temporary situation in the wall where now this negative balloon is attracted to the front edge of the wall because, and you need to say this, because the attraction force between this negative and this positive is larger than the repelling force between this negative and this negative. And this was called an induced dipole, which is a different situation than these. It's very similar to that, but the balloon caused the dipole. If we take the balloon away, this turns back to a neutral situation. So it's really important when you do the explanation that you say something about the attraction is greater than the repelling because they both still exist. The balloon is attracted to the front part of the wall and repelled to the back from the back part of the wall. And you should say that the attraction is bigger because the distance is smaller, like we learned in class. Okay. How many of each kind of atom in the following? Well, that 3 in front we've learned means 3 of the entire things, whatever they are. And we haven't even learned how to name these things yet. That means there's 1, 2, 3 coppers. In each one of these things, there's a parenthesis with a number after it. That means the entire parenthesis happens twice. So this has 1, 2, 3, 4, 5, 6 oxygens and 2, 4, 6 hydrogens. Okay. This one, the entire molecule happens 4 times. Okay, so whatever I get for the individual molecule, I'm going to multiply by 4 because there's 4 total. So one of these molecules has 3 zincs. So that means there'd be 12 zincs altogether. One of these has 2 phosphoruses. 2 times 4, that'd be 8 phosphorus altogether. And one of these has 2 times 4, 8 oxygens. But there are 4 of those things with 8 oxygens in them. So that'd be 32 oxygens. Dash there. This one easier. That'd be 2, so there'd be 6 hydrogens and 2 phosphorus. Okay, so this last section, what charge would be formed if these made an ion? Okay, so the first question is, are they metals or nonmetals? Because if they're metals, they will always make positive ions, and the nonmetals will make negative ions. This is in column 1, and we learned in class that means it makes a positive 1 ion. Fluorine is in column 7, so it's going to pick up an electron to make a negative 1 ion. Oxygen's in column 6, it's going to make a negative 2. Phosphorus is in column 5, negative 3. Aluminum is in column 3, so it's going to make a positive 3.